Stress-strain curve. In this module, you will learn how strain changes with changing stress for different types of materials. When a body is subjected to a deforming force, a restoring force is developed in the body which is equal in magnitude but opposite in direction to the applied force. This restoring force per unit area is known as stress, and the deformation caused is known as strain. The relation between the stress and the strain for a given material can be found experimentally. For this, let us take a spring and stretch it by applying a force. This causes a change in the length of the spring. Now change the force applied and again note the change in length of the spring. Record the fractional change in length, that is, the strain, for the different values of force. Plot the graph between the stress equal to the applied force per unit area and the strain produced. The curve so obtained helps us to understand how a given material deforms with increasing loads of force. From the graph, we can see that in the region between O to A, the curve is linear. In this region, Hooke's law is obeyed. That is, stress and strain are directly proportional. That is, with increase in force or stress, the strain also increases. The body regains its original dimensions when the applied force is removed. In this region, known as elastic region, the solid behaves as an elastic body. In the region from A to B, stress and strain are not linearly proportional. In spite of that, the body returns to its original dimension when the load is removed. The point B in the curve is known as yield point, also known as elastic limit, and the corresponding stress is known as yield strength, SY, of the material. If the load is increased further, the stress developed exceeds the yield strength and strain increases rapidly even for a small change in the stress. It is represented by the curve BD. When the load is removed, say at some point C between B and D, the body does not regain its original dimension. In this case, even when the stress is zero, the strain is not zero. The material is said to have a permanent deformation or permanent set. This deformation is said to be plastic deformation, and this region is said to be plastic region. The point D on the graph is the ultimate tensile strength, SU, of the material. Beyond this point, additional strain is produced even by a reduced applied force, and fracture occurs at point E. If the ultimate strength and fracture points D and E are close, the material is said to be brittle. Some examples of brittle substances are glass, slate, antimony, and bismuth. If the ultimate strength and fracture points D and E are far apart, the material is said to be ductile. For example, aluminium, copper, and steel. The stress-strain curve varies from material to material. This figure shows the stress-strain curve for the rubber. Although elastic region is very large, the material does not obey Hooke's law over most of the region, and there is no well-defined plastic region. Substances like rubber, which can be stretched to cause large strains, are called elastomers. Interestingly, the elastic tissue of aorta present in our heart is also an elastomer. Let's recap. The stress-strain curve varies from material to material. The stress-strain curve of a material has the following regions. Elastic region, where the body regains its original dimensions when the applied force is removed. Plastic region, where on applying force, the body undergoes a permanent deformation. Fracture region, where additional strain is produced even by a reduced applied force and fracture occurs. In the stress-strain curve for a brittle substance, the ultimate strength and fracture points lie close to each other. If the ultimate strength and fracture points are far apart in the stress-strain curve of a material, the material is said to be ductile. Substances which can be stretched to cause large strains are called elastomers.